I completely forgot about that. So yeah, I just turned the record button on. So anyway, so this is my most popular lecture, and unfortunately, you know, and I get a lot of volunteers from the class to come down and actually do a lot of these demonstrations, but unfortunately, we're not able to do that right now. So I tried to do the next best thing, which was to have one of your classmates, Corey, who has been working in my lab for the last year, actually do some of the demonstrations, and I recorded her. So at least there's somebody from your class who has been able to participate, and hopefully the videos will do justice to the demos. Anyway, so I used to ask the class, and I realized that this may not be the best thing to do. Let me see. Oh yeah. So I used to ask the class how many have heard of polymers, but I stopped because many years ago, and if you remember, I've been here quite a while, but many years ago when my kids were small, they were playing Yu-Gi-Oh! I don't know if any of you have is a Yu-Gi-Oh! Player, but played Yu-Gi-Oh! And they had a card called polymerization. So I kind of assumed that everybody knew what polymerization was and what polymers were. And then, of course, I realized that some people actually did have a life and did not play Yu-Gi-Oh! Anyway, so here we go. So that's why we have this lecture on polymers. Now, has anyone had a lecture or course on polymers? You can kind of join the poll there. Oh, no, okay. I don't have a single person who've had one person. Oh, good. Oh, wow. That's a lot, 8. So this, usually I only get like one person who's actually had a course or lecture on polymers. So this is very surprising. We have 11 people who have so far said that they've had something on polymers. So that's wonderful, and definitely will help a lot. For those of you who've taken a course or a class or a lecture on polymers, can you quickly put on the chat whether whether you're an engineering student or what major you are? Engineering, okay. We have one engineering student. Okay. Yeah, oh, so we have several engineers in the dental school. The BME, when I took it, good. Bio major at Lamar, and took a biomedical technology as a biology lecture. Oh, good. That's wonderful. So this actually then should be kind of like a review, hopefully for you. So other than those people who've taken a course or lecture in polymers, I would like the rest of the class to maybe guess some examples of what polymers might be. You can type that on the chat. What do you think might be? Let's see. Impression materials, good. Yes. Well, yes. Anybody else? It can be non-dental, dental, resin. Okay, good. Plastic bags, wonderful. Plastics, good. Long chain with repeating units. Okay, somebody is already knows their polymers. Rubbers, good. Styrofoam, very good. Thank you. Silly putty. Okay. Yeah. So actually, this is probably the most knowledgeable class that I've had on polymers. Usually I only get maybe one person, two people who have actually had anything on polymers. But from these examples that have already been suggested, you can tell that polymers are very prevalent in our culture, in our world right now, right? Case in point, this is the ingredients list of the hairspray that I use to do my hairdo. And you can see on the ingredients list, you have alcohol or denatured alcohol, water, agua, I guess water is a difficult word, ethyl ester of PMMA copolymer. There you go. So they have a polymethyl methacrylate copolymer in there, a fragrance, and some of the other things in there. So what actually makes your hair stay and keep its style is this copolymer. And basically the water and the alcohol are basically solvents for this. And once you spray it on, it evaporates away, and you're left with this shell of polymer that allows you to style your hair. Okay? So even in places and things, we have polymers all over our, or all around us. Okay? Now, in dentistry, the main applications are as follows: prosthesis, restorations, equipment, impression materials, denture liner cements, just to name a few. Okay. So let's begin with a definition of polymers. And somebody already mentioned this. Basically, a long molecular chain with many repeating units. Poly meaning many, mer meaning a unit. Okay. And so basically polymer is, and these mers are called monomers when you have a single mer. And these are chemical compounds that are capable of reacting to form a polymer. So it's not just any molecule, it has to have that capability of forming a polymer. And that's formed through a process called polymerization. Right? So we have here monomer plus monomer plus monomer through polymerization gives you a polymer, as you can see, where the molecules are connected, covalently connected to each other. The easiest, the simplest example is polyethylene, where you start off with an ethylene molecule, and you have the carbon-carbon double bond right here. Sorry about that. And through the process of polymerization, this double bond is attacked and opened up, and so is this one, and they form a bond between each other, and now you get a long polymer, okay, called polyethylene. This is an example of a random coil of polyethylene, and it's just a long chain that just is coiled up, and that's just kind of how it exists in nature, unless it's processed in some way. Okay? So what we just saw was a linear polymer, where it's just you have these mers connected to each other, forming a long chain. Okay? However, polymers can also exist as branched polymer, where you have the backbone chain coming down like this, but you also have branches. And these branches could have been already there. So this particular mer already had a branch, and it just reacted over here, so it gives you a side branch. Or it could the milieu can contain a monomer that has more than two reactive sites, and two or more reactive sites, and so it grew a chain. Okay, so that can happen too. Or the polymer can exist as a cross-linked polymer, where you have all of these backbones, okay, these chains, but they're connected to each other, separate chains connected to each other, either because you had a cross-linker in there, which entered into the reaction right here, and then and connected the two chains together as it grew, or you had a monomer here and a monomer there that had two or more reactive sites, and was able to grow two chains this way and just happen to connect with each other. Okay, And we'll talk a little bit more about that. Polymers can also be formed using more than one type of monomer. So in the hairspray example, we saw that the PMMA, the polymethyl methacrylate, was a copolymer. Now they don't tell us what the other monomer is, okay? But you know, since it said copolymer, we have to assume that there was something else that entered into the reaction. So you could have a copolymer that is random, and you can, where it can be just these white circles are one monomer and black circles are another, but they were able to react with each other because they had the same functional groups. And so you just have this chain with just random distribution of each monomer. They can exist as a, you can also have graphed copolymers, where you know, this is again is random, but again this is a branched copolymer that has just random assortment of monomers in there. Or you could design a copolymer where you can react a oligomer or a small polymer of one type with small polymers of another, and design it so that you have blocks of these monomers in there. This is another example of it where you have a graph copolymer where you have the backbone is made out of one polymer, but the side groups, the branches, are made out of another. Okay, and you can imagine that since these are chemical entities, that a random copolymer can have different properties from a block copolymer, and since you're specifically designing it this way, it probably has some very specific properties, material properties that the designer actually aimed for. Okay, so as you can see, you know, copolymer, branch, cross-linked, and just a regular polymer by itself. There are many, many different possibilities, and you can actually design almost an infinite number of materials based on this. And that's why plastics are also so popular, because you can design those properties. Okay. Now, one of the things all of these things affect is mechanical properties or material properties, right? And we talked a lot about that last week. So, for example, if we just take a straight chain, if we grow that chain, and this is molecular weight, this is different mechanical properties like rigidity or stiffness, strength, melting point, you'll see that as you increase the molecular weight, it can go from a gas to a liquid to soft solid, hard solid, and then a hard and rigid solid. Okay. Now, if you add branches to this, okay, all of those properties tend to increase. Okay. Can anybody tell us why that might happen? Yes, can anybody guess why that might happen? Feel free to use your mic if you have that on, or type in the chat. And also, please don't be afraid of interrupting me if you had questions. Okay, multiple users are typing. More stable. Okay, if you can explain what you mean by more stable. Intermolecular forces, okay. Harder bonds to break, okay. Branches increase the possibility for more, I don't know what VDW divided by IMF is, if you would type that out. Longer chains have a greater chance of forming entanglements. Good. So that's kind of basically what it is, right? So you start off, have any of you did any kind of gardening or worked, did some summer jobs mowing lawns and trimming bushes? I unfortunately had to do that without pay since I was in high school. And if you've ever tried trimming bushes, or even like if you trimmed branches off a tree, and these could be branches with no leaves. Okay, as they fall, they get entangled with other branches, and if you try to pull them out, it's really difficult. Okay, so that's kind of what it is. These branches, are branched out, and when they have neighboring branch polymers, they get entangled. And so when you try to pull them out or move them, bend them, whatever, because of the entanglements, it is more difficult to do that. And that is why these mechanical properties increase, okay, with branched. Now, we can go further than that and have a cross-linked polymer, okay? And in this case, a cross-linked polymer does not exist, or tends not to exist, well, does not exist in gas form for sure, because it has to be really low molecular weight, but often will not exist in liquid form as well, okay? And usually you start off with a gummy solid, and it goes up to soft, hard, and then as the molecular weight increases, a brittle solid. Can anybody guess why it doesn't exist as, or tends not to exist as a liquid? Okay, somebody's typing. Michael is typing. Molecules aren't able to flow. Yes, and the reason why molecules are stronger material, okay? Can anybody answer, or although he typed it as a question, elaborate on why molecules aren't able to flow? Crosslinks keep them from getting close. Yes, actually, it's the opposite, right? So if you have crosslinks and they happen to polymerize like this, right, you can't separate them. And if you have a material, molecules are packed closer together, yes, increase rigidity and strength. So if you have a crosslink material, that means you have to have quite a few monomers already in there. So the molecular weight actually starts off higher in general, right? Because you have to have, a chain, another chain, and a crosslink. So they start off with a higher molecular weight, and we already know that if you have a higher molecular weight, it'll tend towards being a good solid. But on top of that, when you have cross-linked molecules, multiple cross-linked molecules, they don't just necessarily just form separately. They can be already entangled as they form, which would create a much larger molecule. And theoretically, and this is just theoretically, ideally, a perfectly cross-linked molecule in the entire mass of the material would only have one molecule, right? If you were able to ideally cross-link all of the polymer chains together, there would be one molecule. So the molecular weight would be humongous for that polymer, okay? So it's all related to the molecular weight, branching and entanglements, and obviously cross-linking would be the ultimate of the entanglement that we see, okay? And if you look at this, the fact that it becomes brittle here, and not that these are not brittle, they can be brittle if the molecular weight is high enough, but cross-link materials become brittle much more quickly. And again, that's kind of why it is, because they can be locked into each other and they can't flow, like someone said. They can't be drawn. Okay? And we'll talk more about this as we throughout the lecture. Okay. So my first demo was actually a demo of three similar fluids. So when you look at this picture that I have, okay, you have three. I have this really annoying box over my slides, but you have three cylinders of liquids. So let's start off with what are some similarities. And unfortunately, I didn't have enough of the third liquid to be able to fill up the same level. But ignoring that, what are some similarities of these liquids? And I think if you can use your mic, I would prefer that. I think it just might be more quicker. But okay, transparent, good. What else? Volume, transparency. Okay. Now, I don't know if you can see this, but can you read the text on the bottom? I've named them for you. Okay. Any guesses on what might be similar about those liquids? Alcohol. Okay. This is an alcohol. Good. I'm going to go ahead and these are the names of the liquids: methanol, ethylene glycol, and glycerin. Okay. These are the chemical formulas and the molecular weights. What are some similarities and differences then of these?
One of the differences is the number of monomers that are attached to the molecule.
Very good. Very good. Yes. So actually, can you go ahead and tell us what the similarity is then?
They all have a methyl group and an alcohol group on them, but
Very good.
as the molecular weight goes up, it increases the number of groups that has.
Yes, wonderful. Thank you so much. So, yes, so basically, this is a monomer, methanol. This is a dimer, ethylene glycol, and this is glycerin. It's a trimer, okay? And you can see that the molecular weight increases proportionally, kind of, right? So when you look at these materials or these liquids, as far as material properties, what would you expect? What are some things that you might expect? Whether they are similarities or differences?
A difference in boiling point and vapor point and
Good,
just kind of molecular weight properties.
very good. So we learned from the previous, we didn't really specifically talk about it, but from the previous graph, we know that melting point should increase with higher molecular weight. Good. And vapor point, I'm sure you're all aware, alcohols evaporate really quickly, right? You can, if you know glycerin, you know that that probably does not. Good. Good. So some of the material properties were said to increase. Okay. So let's see what these material properties look like. Somebody said it would have the strongest IMF. I don't know what IMF is. But anyway, thank you. Intermolecular forces. All right, good. Somebody said the glycerin looks more viscous. Very good. Okay, so increase in viscosity. Good. Viscosity increases molecular weight. Good. So let's take a look at that. I don't know why my copy function does not work very well, but there we go. So we took a video of me dropping a ball into each cylinder. And you can see that dropped pretty fast. That one a little bit slower. And then when we do this, you can see that the glycerin definitely drops very slowly. Okay. So, and if you noticed, and I don't think it's as obvious through the video, but in real life, there's actually a drastic increase in viscosity. And the speed at which the ball falls to the floor is dramatically slower, right? So these mechanical properties are not necessarily proportional to the molecular weight, but molecular weight definitely seems to have a tremendous impact on the different mechanical properties that we have, right? So now the relative positions, and we talked about, in this case, we have an alcohol group at the ends, but we also talked about having branches and how that affects, material properties. Well, the position of those branches are also very important in how they affect material properties. And this is called tacticity. So it's kind of analogous to chirality in biology, okay? And so R would be the side group that it has. And this is isotactic, where you have the side group repeating on the same side of the carbon molecule, okay? And there are three ways that this can be arranged. The first one is isotactic. The second one is syndiotactic, where it alternates from one side to the other, as you can see here, these side groups. Okay? And the third one is atactic, where it's random. Sometimes it's on the same side, sometimes it's on the opposite side, as you can see here. Okay? And this is important because tacticity affects material properties by how it arranges itself, okay, or molecular orientation. So in the case of isotactic or syndiotactic polymers, because they are regular, they have repeating structures, they are able to stack up on itself, okay, like this, and create these crystalline regions. Okay? And these crystalline regions are highly ordered. They tend to be hard and rigid, higher melting point. They tend to be impermeable because you can see that there's less space between the chains for solvents to be able to get through. Now, they can be transparent or translucent depending on the material, the chemistry, as well as how packed they are in its crystalline regions. However, atactic polymers, because of its random nature, they're not able to form these regular arrays. And instead, they form these amorphous regions, like the polyethylene that we saw, although that is not an atactic molecule. It's just, it doesn't have any side groups, right? It just has hydrogen. But they tend to be amorphous regions that are just kind of randomly coiled. Okay, so random coils. They tend to be soft and flexible below the glass transition temperature, which we will talk about, or glassy. Okay, and when I say glassy, you might not tend to think of polymers or plastics as glassy, but if you think about plexiglass, that is actually not your silicate glass. It's not a borosilicate glass or anything like that. It's made of polymers. But because it's below the glass transition temperature, its material property, the property it has, seems like a glass, okay? So that's what it means by glassy. It absorbs a lot of liquids. It can absorb a lot of liquids because you can see all of the gaps between the chains. And also because they're not ordered, they can be transparent, okay? However, these are kind of like ideal conditions because in reality, we have a combination, and all polymers, you can have a tremendously amorphous polymer, but most polymers are semi-crystalline, where you have some regions of order and some regions of amorphousness. And depending on how the proportion of these two types of regions, you'll get properties that are more similar to a crystalline polymer or more similar to an amorphous polymer. Okay. I want to show you a video of this. So this is a spherulite or a polymer that is coming down from a melt. Okay, so it's melted and it's being cooled, and as it solidifies, because this is a crystalline polymer, it'll start at a point and then create these spherulites where it folds upon itself like this, and it grows out. Okay, and what we're looking at is under polarized light, we're able to see all of these colors. Okay, and that's because of the crystalline regions refracting light. Okay? So you can see that grow as it is coming out of a melt and becoming a solid. Okay, and that's how you get a solid, right? Um, so my second demonstration is actually using a plastic strip, and you can do this at home just to see what it feels like. This is Corey, by the way. And so this is actually a demo that I used to show my brute strength as well as finesse. And I asked for several volunteers to come down, and male and female, strong and not so strong. And uh, we have a little competition where the students come down and I give them these plastic strips, and they start to stretch it. And the competition is to see who can stretch it to the longest uh, um, strip possible. Okay, and I can tell you without bragging that I've never lost this competition. So this year will be the first time I'm not able to demonstrate that, but Corey has done a wonderful job, and so I wanted to show you how. And if you listen carefully, she's going to try to tell you what it feels like as she is stretching. So listen to that. Okay, good. Uh, So then, after the students do that, we measure how how long it is, and then I come on, and this is what I do. So here, what I'm doing is I'm going to pull. These are uh, polarizing lenses, just like your polarized lenses in your glasses, and you can see initially back here that each individual layer, the light actually transmits through this, albeit tinted, right? But once I put them together, you can see that no light comes through this. Okay, so basically, your polarized lenses, what happens is that in your sunglasses, as light reflects off of surfaces, like and causes glare, they come in an ordered way. And what polarized lenses will do is, those lenses are kind of like oriented this way, right? Just as an example, and they would cut out light that is coming at a certain angle. So that's kind of what this does. So when you have one lens, a lot of the light can come through. When you have two that are oriented like this, and they're on top of each other, it is able to block out all of the light. Of course, your sunglasses are not like this, right? You're trying to cut out lenses that are light that is oriented in one direction after it's reflected off of surfaces. So anyway, that's Polaroid lenses, polarized lenses. And watch what happens. So the first thing is you notice that as I put that strip between the lenses, there's more light coming through. Okay, and this is when I hear a lot of ooh, ah in the class. Thank you, Elizabeth. So what happened there? As I pulled the strip, okay, well, let's start off from the beginning. When I stuck the strip in there, why did it all of a sudden let more light through? Okay, good. Bailey says, did it change the angle that the light is reflecting? Yes, I would just change the last word to refracting. Good. So the light came through. Let's just say, I mean, this is not correct, but let's say the first lens was angled this way, and the light comes through. Okay. Only light that is oriented in the same direction is able to come through. Okay. And when you have a second lens like this, then obviously nothing gets through the second lens. However, if the strip, the polymer strip that came in, because of whatever orientation the chains were, that was able to refract the light a little bit. And so now the light coming in was no longer like this, but refracted this way. And the component that was this component was able to get through the second lens. Okay, so good. So that's a good start. And then, as you saw, I was stretching the strip, and then we started. Hopefully, saw that you start seeing a lot of different colors. Now, why do you think that happened? Any guesses?
As you stretch the plastic out, did it change the kind of light that was refracting through because of like the thickness of the plastic going down as it was stretched outward?
You're almost correct. Okay, Azusana, is that correct? Azusana says the different wavelengths absorbed. Okay, Shirin says thickness decreasing. So thickness decreasing, yes, we did see that, right? We saw something called necking, and the thickness did decrease, but and then Azusana says different wavelengths were absorbed. So how does the thickness, and more specifically, how did the material absorb different wavelengths? How do you think? Think about what we've just been talking about, right? Molecular orientation. When it changes orientation, cross-links pulled apart, more light passes through. Okay. Weston is still typing. So, okay, orientation of polymers influence the way light is refracted as it passes through. Okay. So, when we look at the reflected waves from both surfaces interfere to cancel each other, not quite. But these are all good guesses. But what? So, you know what? I'm going to add back a colors lecture eventually, because this has to do with color. The reflected waves from both sides. Okay. Anybody know how color is formed? Somebody said, is it because pulling them apart creates more order within the chain structures, changing the way? Yes, yes. But anybody know how color is formed? Light seen is reflected. Good. Reflection of light. Okay. That's actually only one part of it. So what happens is that the color is much more complicated than we understand and absorb. Good. So when light comes, let's say we have this perfect white light. Okay. That is where all of the wavelengths of visible light are the same. That's when we get a perfectly white light. So when that light hits a surface, like it was said correctly by several people, some of the light gets reflected, but some gets absorbed by the material. And when we say some are reflected and some are absorbed, we're talking about wavelengths. So some wavelengths are reflected, and what we see are the wavelengths that actually are able to come back, because the other wavelengths are absorbed. Okay, so the differences in the intensities of the different wavelengths is what creates light. Now, unfortunately, red is not just that we see, is not just one wavelength. Okay, a laser red would be one wavelength. Okay, but the light that we normally see in life is a mixture of different wavelengths, and that's why when you hold two red things together, they're almost never the same. Okay, so because of that, so in the color that we see in general, there are more than one wavelength. Okay, so what does this have to do with what we just saw? Okay, so if color is created by wavelength, okay, that means that what we were able to see as I was stretching that strip, the red, the green, all had to do with the wavelength of light that was able to come through. So the cross polarizers have already been cutting out a lot of light, and the light that came in and hit the plastic was refracted. But at the same time, the molecular chains, as they're being stretched, are being pushed together, right? They're being pushed together. And the gaps between the molecular chains is what is allowing light to get through. The light that was able to get through have to do with wavelengths that are smaller than that, or in some multiple of that gap. Does that make sense? So we're able to see light based on how narrow or how close the chains are together. That's why it went from, I think it went from red to green, right? And then back to red, back to green, because there are just multiples of that wavelength, okay, that we're able to get through. So what that refraction, or what all that color was telling us, was how close, how crystalline the material was becoming. Okay. Now this was probably a polyethylene plastic. I don't know, just a plastic bag. So in that situation, yes, they are able to form crystalline regions, but obviously it didn't form as it was being made. Okay, this was artificially induced crystalline crystalline regions. So as Corey is pulling it, the first thing she noticed was that it was really difficult to start. Okay, and the reason that happens is because initially, okay, we have to assume that this material was very amorphous because it's very transparent. You have a lot of elastic deformation. Okay, and if you remember from last week, elastic deformation means that you pull and it'll go back. Okay, once those chains were allowed to slip, then they were able to flow a little bit better, and you actually get plastic deformation. Okay, and at the end, it became really difficult, and some people said, I think, intermolecular forces. But as you have all of these chains lined up together, you can imagine all of the secondary valence forces that are now able to come into play. And now you have all of these atoms next to each other, molecules next to each other. And that's what creates that stronger mechanical property before she's able to break it. Okay. Interrupt me if I'm going too fast or if you don't understand what I'm saying. Okay. But that's kind of what happened. So from this, as I just said, we can gather three types of mechanical properties from polymers. The first thing is elastic recovery, which we learned before. In this case, it's easily deformed but rapidly recovers, occurs in the amorphous regions. And in this case, I don't have that animation here to show you, but when you stretch it out, they uncoil, but then they come back and coil up again. Okay, that's elastic recovery or elastic deformation. And then the second part was the plastic deformation, right, where it's deformed and it can be molded, and the deformation is permanent, the chains do not uncoil, but they actually slip past each other. Okay, and it's irreversible. Once it slips past, you can't get it to unslip. Okay. Now, in the case of polymers, as you saw with this demonstration, you have viscoelastic behavior. Viscous meaning plastic, and elastic meaning elastic. Okay, so it's a combination of both. Okay, so both plastic deformation and elastic recovery. Okay, so and it applies to most polymers, and they're affected by chain length, cross links, temperature, rate of force. Okay, and what you have is as you stretch out, first it uncoils, then it starts to slip, and then it recoils a little bit when the force is taken away. And if you think about our stress strain curve, and you have this curve that goes like this, it's initially it's straight, you have the elastic portion, and then it deforms. That's kind of what viscoelasticity is, and polymers all have that kind of a stress strain curve. Okay. Now it says here that it's affected by rate of force, okay, the viscoelastic behavior. What do you think that means? The fast force, yeah, okay, yes. So yes, so the rate of force means how quickly you apply the force, yes. Why do you think, I'm sorry, let me re-ask the question. That was not a good question. So Jennifer says it's time dependent, yes. So how do you think the rate of force, how quickly apply the force affects mechanical behavior? What would you expect to see? If you pull it real fast, it could break earlier. Okay, so we're talking impact force, yes, yes. Jennifer says deformation. Can you elaborate on what you mean by that? How quickly we apply the force affect what kind of behavior we see? Long-term force would more likely create a more significant plastic. Very good, very good. Ishan says, basically says that if we put on a force for a long time, it will most likely create plastic deformation, the chain slippage, good. Creep or flow apply, yes, very good, Bailey. What happens if we apply the force quickly without breaking it? Slower rates give it more chance for plastic deformation, yes, because it gives more time for secondary forces to occur, good. What happens if the rate of force is fast? Elastic deformation, good, yeah. So depending on how quickly apply the force, the material can actually behave elastically, more elastically, and if you apply the force slowly, it can behave more plastically, okay? So that's what viscoelastic behavior has. It's basically both types of mechanical properties are existent there, okay? This is just a schematic of what just happened here. As you have these amorphous regions and you pull together, okay, you start to orient the chains and give it a crystalline orientation. Okay, good. So to show the viscoelastic behavior, okay, I'm going to show you another. I don't even know why I call these demonstrations, but you know, another demonstration. In this case, we're going to cure polymethyl methacrylate. Okay, polymethyl methacrylate is widely used in dental materials and in medicine. So PMMA was, and we'll talk a little bit more about this, I think, our next lecture, which is several weeks down the road. But it has applications as impression trays, denture material. Really, that's the big application for dentistry. Bone cement in orthopedics. But polymethyl methacrylate really is like the basis for where we have how we developed composites for filling material. Okay. Anyway, PMMA polymerizes through a process called addition polymerization, which we will talk about later. And as it polymerizes, we're able to actually see a whole bunch of different material properties. Okay, so I had Corey, who's been doing some research with me on developing an antimicrobial polymethyl methacrylate denture material. And so she's an expert in making this. So I have a little video of her doing different stages of this. It takes a long time to have this cure. So a lot of times I have students come in front and they start mixing it, and then we actually don't get to see the results until much later. So maybe the video is a better way of showing this. But so initially, you have Corey mix the powder and liquid in about a 3-to-1 ratio. Okay, and this is a product called Lucitone, which is a denture material. And so you can see that as she mixes it, okay, this is called the sandy stage. So, what you have there looks like sand on the beach, literally, and if you just pick the sand up that's wet, that's kind of what it will look like. Okay? So this is just the wetting of the polymer beads, which is the powder, with the monomer, and it's got other chemicals in there to start the polymerization. Okay. Then, if you wait a while and it polymerizes, okay, and it polymerizes, the next stage is that you get kind of like a very sticky, stringy stage, okay? And it's just kind of, it's just very plastic. It strings out, it's sticky, okay? And then the next stage, hold on. That's the next stage here. This is the next stage, where now we have more of a dough. You can see it's not very sticky. And you can see a lot of plastic deformation as she pulls it, but it's not as like sticky per se. It doesn't stick to her hands. It's kind of like dough that you would play with when you're baking. And watch as she rolls it up, and you know it's like silly putty, right? She pushes it down. It's all plastic deformation. Okay. And so now she's going to roll it up into a ball, and she drops it. Now you can see that even though she dropped it, it doesn't plastically deform, right? It's the rate of force is causing it to act elastically like a rubber ball, okay? Then the next step we see as it continues to cure is this. Now, it's already polymerized quite a bit, right? And we're in the rubbery stage where you can see that she's pushing it down, but it bounces right back up, right? It's still a little bit plastic, but you can see it's very, very strong. And the plastic deformation is much more difficult to do. And as it breaks, you can see how it just kind of elastically goes back, although not back to its original size. But it does feel like, a piece of rubber band or something like that, right? And so this is the rubbery stage. And then the final stage is when the material has fully cured. Okay. And you can see it's like a golf ball. It's really hard. All you get is elastic deformation. She cannot deform it anyway. It's very hard, very kind of glassy type of a material. Okay. So there you have it. So as you have the molecular weight increase, we're able to see a range of these properties going from something that is, really not very solid, like the sandy stage, to something that's very, very plastic only, and then you get more and more elastic behavior, especially as you apply different types of forces. And then it gets to the point where it gets completely elastic, hard, rigid, elastic, based on molecular weight. Okay? So in the middle is when you see a lot of the viscoelastic behavior. Okay? The next property to look at then is dissolution properties. Okay? Polymers, they, especially when you have a higher molecular weight, they tend to absorb and swell solvents or liquids rather than quickly dissolve. Okay, and so if you have a low molecular weight polymer, of course it can dissolve, but as you increase the chain length, the dissolution time increases, and it'll tend to be more swollen rather than dissolve. And if you have a solvent, what will happen is it can actually get between the chains and cause it to plasticize, so it might soften. And then when you get to a point where you have a lot of cross-links of very, very high molecular weight, or preferably cross-linked polymers will not dissolve. I told you that in the ideal case, you could actually end up, you really can't, but in the ideal case, you would end up with one molecule, this big mass of one molecule, and there's no way that's going to dissolve in anything, right? But taking that extreme a little bit less, to a lesser degree, you would have very large molecules cross-linked that really cannot dissolve, because the dissolution process does not, unless there's a chemical reaction breaking the bonds, it really does not break the bonds that it has. Okay, so we say that elastomers swell more than plastics. Okay, so why do you think that's the case? Any guesses? Even if you don't know what elastomers are, since we're contrasting that with plastics and elastomers, take a guess as what that means. And by the way, people tend to call polymers plastics, but that's not a very good term, is it? Right? Because some polymers will act elastic, right? So plastics is more of a layman's term. It's not a very correct term. But anyway, no guesses? So if we assume that elastomers means a polymer or polymeric material that is very elastic, rubber band or something like that, and plastics are something that are easily moldable, like putty, okay? Elastomers they tend to swell more because they have more and elastomers would be also more cross-linked as well. So they don't dissolve as easily. And so they're able to hold together better, but also because they are, they have a lot of space in between. You can imagine that they're probably not very crystalline. There are a lot of amorphous regions that are able to allow that to happen, right? So for my next demo, okay, we're going to look at crystal soil, okay? This demo, I actually had a different demo before, but one of your colleagues from the class of 2017, Kristen Rodriguez, came to me one day with the crystal soil and said, Dr. Wine, this is a wonderful demonstration of polymer swelling. And sure enough, it was. So crystal soil is made by using acrylamide monomer and polymerized into polyacrylamide. Incidentally, the same material, although not in its same form, is used in diapers. So if you know anything about diapers, basically they absorb a lot of water, right? That's the whole point of having a diaper, right? And so crystal soil is used instead of soil to hydrate the plants. And when you place it in water, it can absorb 80 to 150 times its volume in water. Okay, so I have a little demonstration of that here. So this is crystal soil, and you can see how small it is. And if I drop it, it's I don't know if you can see that, but it's completely elastic. It's very hard, very glassy kind of a material. Okay. Now, again, with this demonstration, you would need to leave it in water for a while. But if you did leave it in water for a while, this is what you would end up with. Okay. So I usually have a lot of fun with this because I get to throw it at you. But unfortunately, I don't have that luxury today. But you can see how that little bead has become these balls. And as you can see, when I crushed that, it just broke apart. There's some water can come out, but there's no water gushing out. It's not a balloon. it just absorbed all of the water into the bead and just grew, okay? And it became very soft and hydrated, right? So that's polymer swelling. The next property, the final property we're going to talk about for polymers today is thermoplastics. Thermal properties. And for polymers, they exist in two types of thermal polymers. Okay, first type is called thermoplastics. Okay, and what that means is that when you heat it up, they become softened. They become softer. Okay, and when you cool it down, they get hard again. And we talked a little bit about this before with glass transition temperature, which we will look at in a bit. But you know, if you heat it up, it gets softer. When you cool it down, it gets harder. You can mold it when it's heated up. Okay, and if there's a way of molding it back to its original shape when it's heated up, and you cool it down, it'd go back to that. All right. So it's reversible in that sense. There are no chemical bonds that are formed, right, during this heating process. However, another group of polymers are thermosets, and these are cross-linked polymers. So they're kind of called thermosets because they can be formed or they can be cross-linked using heat as an acceleration for the polymerization. So if you did that, then you would have a liquid or a soft solid, and you would mold it into shape. Then you'd heat it up. Then it would polymerize and cross-link. And then when you took it out, you would have a definite shape. And even if you heat it up again, you cannot soften it. Well, it's soften a little bit, but you cannot have it plastically deform. Okay? It'll just hold a shape. And that's because the cross-linking bonds the neighboring chains together. And so you can't flow the material. And this process is irreversible. Once you set it into a certain shape, you can't unset it. That's why it's called thermosets. And so those are the two types of materials that we tend to see. Now, as we describe this more, I mentioned a little bit about glass transition temperature. Okay. Basically, that's the transition from glassy to rubbery state. It's very important that you understand that it is not melting. Okay. In a technical sense, the actual definition of glass transition temperature is a sudden alteration in the rate of change of specific volume. So let me illustrate that with this graph. So specific volume, okay, and you have temperature here. So as you heat something up, everything expands, right? The molecular motion, and increases and it starts to expand. With polymers, especially well, the semi-crystalline and the amorphous polymers, they all have very pronounced glass transition temperatures. What you see is that they start to expand, and then as soon as you hit glass transition temperature, they will expand much more quickly. But you can see that there's a coefficient of expansion, and this coefficient goes from a low coefficient to a high coefficient. Okay? It means it expands more after the glass transition temperature. Okay, so that's kind of the scientific definition of glass transition. But for us, what's more important are subtle mechanical property changes, okay, that occur along this. So again, this is specific volume and temperature. But if you look at it, as we heat this up, you get from a very hard glassy material to a softer glassy material. Once we pass glass transition, we get a leathery material, and I mean leathery, like what you would normally feel when you hold a very thick piece of leather. And then it becomes rubbery, and then a semi-solid, and then a liquid. Okay. We can map this to a modulus, and if you remember what modulus is, it's how stiff a material is, the steepness of the curve, the slope of the curve, of the stress strain curve. You see that the modulus is really high, it's glassy, very stiff, right? And then you go past the glass transition, and then the modulus drops, and you can have, it becomes very leathery, and then becomes rubbery, and then it'll flow, okay, into a liquid flow, right? So glass transition is here, and liquid flow is down there, so it's not the same thing, okay? If we map this to molecular processes around glass transition, you can see that initially you just have bond bending and stretching, then you have movement of the side groups, and then the chains start to coil and uncoil around glass transition, and then chains start to slip, and that's how you get flow. Okay. So for my next demonstration, I used to do a demonstration with suture material. Polylactic co-glycolic acid is a suture material, and what I did was I made a really nice puck out of this, and it was a very glassy puck. And I had students come down and try to break it or bend it, which they couldn't. And then I left it in a 60-degree water bath. And after that, you can see that it was very leathery. Unfortunately, one year I had this really buff guy, almost as strong as me, and came down and he actually broke the thing. So I no longer have this demonstration. However, I realized, and then so as I contemplated what else to do, I came across this video, and I actually realized this was a better demonstration than what I had, and so we can watch this. So I don't know if you are old enough to know this movie, but it was Spider-Man. For those of you who've seen this, is one of the older ones. My question is, what happened there? What happened in that clip? Anybody? What happened?
In that clip, they froze him, and then since his body was frozen and wouldn't, like, I guess, elastically bounce from those bullets, it shattered whenever it was given direct force.
Okay. Can anybody add to that? My first question when I saw it was, who on earth has liquid nitrogen flowing through the pipes in a building? Have you ever thought that? I'm thinking like, why would there be liquid nitrogen there, right? Which it was apparently. Can anybody add to or comment on what? I'm sorry. Was that Kevin? Was that Kevin?
Yes.
Thank you. What Kevin said? Okay. Michael says it became brittle. Good. Anything else? Well, was that freezing? Oh gosh, today it's like clicking off all the time. Oh, you know what? I'm sorry. It's already 9:11. I completely forgot about giving you guys a break. Let me just finish this demo and then I'll give you guys a break. I'm really sorry about that. Time flies. Was that freezing? Yes. Alphonsus says yes. Anybody else? You know what? I am going to start a poll here. Okay. Was that freezing? Give me a vote. I like this polling thing. Okay, the yeses are winning out 5 to, oh no, the no's are winning out now. 6 to 10 to 6. Oh, got a pretty even competition here. Oh, that was fast. 43 yeses, 51 no's. Come on, those of you holding out. 52 no's, 45 yeses. 54, 46. Got 5 more people to vote. 56, 46. Kevin, why aren't you voting?
I have 2 of mine up, so I have one on my computer and one on my iPad.
Okay. All right. I'm like, you're the one who said it and you're not voting. Okay. All right. So, Christian, you haven't voted. Okay. I am going to publish the poll. So the nose barely eked out the win, 57 to 47. Okay. And okay, somebody from one brave soul from the nose, tell us, why did you say no? Why is it not freezing? Why is it not freezing?
This could be totally wrong, but in the past, I've learned that freezing is from a liquid to a solid. So he wasn't a liquid monster, so he wasn't really freezing. Though if he did have liquid blood, that part of him would have been freezing, but the outside organs weren't liquid. So that's why I put that he wasn't frozen.
Excellent. You're absolutely right. The definition of freezing is going from a liquid to a solid. Okay. And yet the monster, at least the skin part of it and the flesh part of it, was not all, but it was solid, right? So hopefully that tipped you off. What happened? If it's not freezing, what happened? Okay, Ava is typing. Glass transition, very good. So it went from a literally leathery material, okay, to a brittle, hard, solid, glassy material. And that's why when the cop or whoever shot the monster, it shattered. That was glass transition. Okay? So I hope one thing you realize is that I talk a lot about what we about the words that we use in our everyday lives, and a lot of times those are actually not correct. Okay, in the true sense of the word, right? So this would be one of them. Normally we would say, "Oh, the monster's hand froze," but in reality, it didn't freeze. It went through a glass transition from a leathery solid to a hard, glassy solid. Very good. Okay. So as we move on, next we're going to be talking. Okay, as I promised, I'm going to give you a 10-minute break. I apologize for forgetting to do that. So it's 9:16. Let's take a break, and I'll give you a 15-minute break. Let's resume at 9:30 so that you can get a cup of tea or something like that. Okay? All right. So for some reason, I have lost control of my presentation. Let me take it there. Got it. All right. Okay, so I'm back, and I hope you are too. So actually, the last part of the polymers lecture is chemistry of polymerization. And we're going to start off with addition polymerization, which is what polymethyl methacrylate does, right? And there are 4 steps to this polymerization process. First one is activation, and basically you have an initiator, okay, something that can actually form a free radical, and in the presence of heat or in the room temperature, an accelerator, or light, in the case of dental composites, okay, it's able to become a free radical. So with our polymethyl methacrylate denture material, the initiator was benzoyl peroxide, okay, and it had an accelerator, okay, and that actually caused it to become a free radical. The next step then is the free radical then attacks a monomer, methyl methacrylate, and becomes an activated monomer. You can see the free radical, at the end of the monomer. Then the next step is propagation, where the activated monomer attacks another monomer, and then this chain starts to grow. And finally, you have termination, where two activated monomers or polymers happen to bump into each other because they have two free radicals, and they react with each other and they terminate the reaction. Okay, so that is addition polymerization. A second type of polymerization is condensation polymerization, and these are the two main types. There are some other, but condensation polymerization is also called step growth polymerization, because in this situation, it's not like you grow a chain. It's whenever the reactants are there, they just react together. Okay, so they react in one step. The monomers react simultaneously. In this situation, a catalyst is used, and usually, not always, but usually, small molecules are condensed out. For example, water or hydrochloric acid. And so that's why the name of the polymerization is condensation polymerization. This is an older name. The more scientific name is the step growth polymerization, because there are some reactions where you do not have any condensate. Okay. So my last demo for this lecture is the nylon rope trick. And basically, nylon is made when you react subacyl chloride and hexamethylene diamine together in the presence of sodium hydroxide, and you actually form nylon, a polymer. Okay, and you have a condensate, which is sodium chloride, and of course, there's water left over. Okay, so one disadvantage of this polymerization reaction is that if you have condensed byproducts, and if that is able to evaporate, then you can cause porosity and shrinkage. If it stays there and does not evaporate, it can actually plasticize the polymer. Okay, so that's a disadvantage. Okay. So here is the video of the demo. And we actually do this in class. So I'm pouring in subacyl chloride in chloroform, and I quickly pour in the water phase, which is hexamethylene diamine in sodium hydroxide, which is in DI water, distilled water, or deionized water. And you can see from all of the smoke that something is happening there as I pour that in slowly. So one of the things I do need are actually quite a few people to help me with this demonstration, as you'll see in a bit. Okay, Samar, I did start the recording, so I hope that worked out for you. Sorry to see that, Nate. Anyway, so here, what I want you to see is we have two layers. Okay, we have the water layer, water phase, and the organic phase here. And we have this kind of cloudy interface here, okay? And if you were to look into it, you might, and it was visible, you'll kind of see like a web or something like that, all right? And normally I have the students come down, and this is what they would do. So you can see from this video that you can pull that web out, and it forms this string or string. And as you pull it out, what happens is that the two interfaces, the two different immiscible layers, they create, as you pull that web out, you create a new interface. Unreacted reactants now are able to react again, okay? So it keeps reacting as you pull it out and forming this polymer, okay? So usually, we get a pretty good length of this polymer, but in the class of 2016 kind of outdid themselves. And you can see as we continue to pull it, it just got longer and longer all the way to the edge, and then longer and even longer. And we actually ended up looping the entire class. And there were still some left after that, okay? So that's polymerization for you. Unfortunately, we weren't able to do this live. I actually gave a free question for the class that would set the record, but maybe I'd be able to do that next year, okay? So that was polymers. It's kind of an awkward place right now since we took the break earlier. But are there any questions before we move on to our next lecture? No? I don't see anybody typing. Okay, so let's continue then and move on to our next lecture, which is the first application of polymers, and that's dental waxes. So the only reason we talk about dental waxes first is because that's what you, I think, have already started playing with in your the lab component, right, of the dental anatomy module. So hopefully this lecture will help you understand what you are using. Well, we'll get to some of the other finer points as we talk about this. Okay, so dental waxes. Dental waxes are very widely used. They soften when heated, solidify when cooled. Well, that's just what we learned about polymers. Okay, they can be readily molded without cracking, which is something that I will be talking more about. It's a kind of a unique property of waxes. I do not believe you get to see this in your current lab because you are doing the, I think it's called the drip wax technique, which I was a little surprised when I first found out because that's not how you're supposed to mold your wax. But anyway, I think it's for whatever purposes you're doing right now, that's what they're using. They can be easily polished or flamed to a gloss. They're non-toxic, and they can be carved to a very smooth surface. Okay, and you can see here a wax pattern of a crown that's being waxed up right now. And you no longer do casting investments or investing this with casting investment material in your education anymore, because those are usually done in the labs. And I do not teach that anymore, but basically you would put in a casting investment material, and then you would burn out the wax, and then you would be left with a positive image of the wax, which you would then put in like gold or something like that, force that in here to fill that gap in that shape. Okay, just a quick description of that. But anyway, waxes are used for that as well as other things. Okay, so waxes are moderately large hydrocarbons. Okay, they are polymers technically. But a lot of times when we talk about polymers, we talk about polymers with higher molecular weight. A small molecular weight polymer would be called an oligomer, usually about 10 repeating units or so. Okay, waxes are relatively large hydrocarbons. They are larger than oligomers, but they are not often referred to as polymers. They have weak intermolecular forces, and which gives rise to some material properties like very large thermal expansion, a very low yield point or yield strength, poor dimensional stability. And incidentally, before I move on, I just want to talk about this word stability. So throughout my lectures, you will often come across the term stability and accuracy. Okay. The difference is that accuracy is when you first make something, it comes out accurate, okay? That it represents what you want it to make, size, shape, surface detail. Stability is you made it, and over a period of time, the dimensions don't change, or they change, right? So that's the stability part. So stability is over a long period of time. Accuracy is as soon as you make it, right? So waxes have poor dimensional stability. and their chain length is too long for high crystallinity, so they're not that strong, but they're too short for high entanglement. Again, that's why they're kind of weaker than a lot of the polymers that we normally think. So the simplest of waxes are the alkanes, okay, which is polyethylene, right? But in this case, it would be a very low molecular weight polyethylene. Okay, so the chain lengths are generally larger than 17 repeating units. Okay, and at that point, you get a melting point of about 22 degrees Celsius. But they're not the only polymers that are in waxes. You have esters, which has ester groups in the middle. Okay, you have, and these are the most common in dentistry. You have alkanols, where you have an alcoholic hydroxyl group at the end, or alkanoic acids with carboxylic groups at the end. Okay, so you know, you can have mixtures of this. Mostly are esters and these alkanes. Okay, and that's what gives rise to waxes and their kind of unique properties. Okay, so overall, waxes can be categorized as natural or synthetic. And among the natural waxes, you have mineral waxes, okay, where paraffin is the dominant one that's used, and that's obviously what you use for candles, right? And they're mainly linear and branched hydrocarbon chains. Another very popular natural wax is plant waxes, and one of them is carnauba, which is very strong for wax and is used a lot for waxing cars. Okay, these are mainly esters, hydrocarbons, alcohols, and/or acids. So they have a mixture of all of these different types of polymers. Okay, and it is one of the main components of dental inlay wax. Okay, there is also insect waxes, and this is like beeswax, and that's kind of where we get the name wax from. And as you can see, you know, there are just various different forms of waxes in nature. Okay, and one thing to understand about these waxes is that it's not like a polymer where you only have one type of molecule. Okay, waxes have a variety of different polymers in there, as well as other additives in there as well. And that's why they behave differently from some of the polymers that we have, or synthetic polymers. And so the other type is a synthetic wax. The advantage, of course, is the uniformity in chemistry, and they're also much larger polymers, so they'll be stronger. However, that's kind of not what is needed as far as properties for dentistry is concerned. So they really have very little utility as far as waxes in dentistry. Okay, polyethylene again it would be an analog to paraffin. Okay? So when we look at dental waxes, okay, there are two major classes of dental waxes and a third minor class. Okay, the first major class is pattern wax. Okay, and like the name suggests, they are used to create patterns. Okay, form general predetermined size and contour for restoration. Okay. Disadvantage of these waxes is that they have thermal dimensional change. In other words, they're not very thermally stable, and they tend to warp upon standing. And that's because they have to be able to reproduce very fine detail. So they need to be softer than some of the other waxes. Okay. Another type of pattern wax is so the first type of pattern wax is the inlay wax. Okay, and you can see that inlay wax is being used here to wax up a crown. Okay, using gold casting of inlays that I kind of briefly described to you earlier. Used, for crowns and bridge units and so forth, and they're used in this lost wax technique where you invest it and then you heat it up and all of the wax is lost. And then you put in the metal or metal alloy to create the pattern. Okay? The second type of pattern wax, and these are kind of straightforward. They're in the The details are all in the handout, so I'm kind of moving past these pretty quickly because they're not really concepts. But the second type is the casting wax. And as you can see, these are used for metallic frameworks of removable partial dentures. And you can see here, how this has been waxed up for a denture framework. Okay. And again, this also uses the lost wax technique and casting investments to make a metallic framework like this. Okay. And they're used for indirect applications. So casting waxes can come in different forms. You have these preformed bars, or they have meshes. They also come in clasps and different retention forms, so it just makes it easier to make those patterns. The third pattern wax is the base plate wax, and they're used in full denture construction, and they're used to establish the vertical dimension and plane of occlusion, as you can see, used in here and over here as you create these dentures. Base plate wax can also be used as a bite rim, as you can see here, to restore the occlusal relationship, register arrangement of teeth, check the denture inside the patient's mouth, and so forth. The second class of dental waxes is processing waxes, and this is boxing wax, which is used to form this dam around this impression, and you can pour in the stone in here to form the positive impression. You also have utility waxes. These are used in many different applications. You can use to be trays, extend trays, build up the edges when you put in the impression material and so forth. And they can come in both stick and sheet forms. The third type of processing wax is a sticky wax. And here, it can be used for temporary holding of broken dentures, for repair and things like that. But the unique thing about sticky wax is when you melt it, it's really sticky. And then when you cool it down and pass the glass transition, or I'm sorry, when you go cool it down, it becomes very firm and brittle. Another form of processing waxes is the blockout wax, and it's used for filling these undercut regions, areas in the cast during processing of the framework. And then the third minor class of dental waxes is the impression waxes. Okay? And the first type is the corrective wax, and you can see that it's used to correct impression technique, using the corrective impression technique, and used to restore regions and so forth. And you can kind of read this by yourself, right? Impression waxes and can also be used for bite registration, as you can see here. Check the occlusion and things like that, and before the bite and after the bite, and so forth. So dental waxes not only have these polymers, but they've got some other additives as well. So you have the gums and fats and resins in there. And gums are generally plant products. They're viscous, amorphous, and they harden when they're dried. They're a mixture of hydrocarbons, so other kinds of polymers. Okay? Fats are just basically glycerol and some other fatty acids, and they're mainly used to modify melting range and to soften paraffin. And resins are plant products that are used to modify melting range, hardness, adhesiveness, flake resistance, gloss, and toughness of the wax itself. Okay, so you can see the composition is very complicated. Every company has its own proprietary composition to adjust the properties of waxes, and it gives rise to very unique properties, as I keep mentioning. Okay, so what we're going to focus on most of the time on is different physical and mechanical properties of waxes. Okay, so we'll look at melting range, solidification, shrinkage, and all of these. So the first one is melting range. We learned that as you increase molecular weight, okay, polymers, the melting point of polymers will increase. Okay, but when you have a mixture of polymers, there actually no longer is a melting point. And in waxes, what you see is a melting range. So this is paraffin, and this is carnauba, and this is a mixture. You can see that this is a differential thermogram, and you can see that there's an endothermic process happening here as you increase temperature. Basically, this is where melting is happening, but instead of a sharp peak, it's broad. So over this temperature, the wax is melting. Okay, even though this is just paraffin, because of the different types of hydrocarbons that are in there, okay, you'll see that. And with carnauba, it's even wider. And when you further mix these waxes together, you can see that the melting range also widens dramatically. Okay, so it starts melting here and it ends melting there. Okay. So if we look at this, you have the composition of the wax. So you have no carnauba, 100% paraffin, 100% carnauba here. And as you add more carnauba into the mixture, you'll see that the melting begins when it's 100% paraffin at, I don't know, 43 degrees and ends at like 61. Okay. But as soon as you add a little carnauba, that melting range further widens. Okay. And with as little as maybe 12% carnauba, I mean, the melting range is from 40 all the way to like 89 degrees Celsius, okay? What is interesting is because carnauba does not actually, 100% carnauba does not melt until 50 degrees, between 40 and 50, you actually do not physically see a melt, okay? It's still solid, but it actually has begun melting. Okay? You just can't see it yet. And it's when you pass 50 that you start to see it liquefy a little bit more. Okay? So it's a little bit different from what you normally think of as melting. And it's not like an ice cube where, you know, you get past 0 and you just wait at like 2-3 degrees Celsius. You just wait and it'll eventually melt. It's just melting slowly. No, here, because there is a portion of carnauba that actually does not melt, you actually do not see the melt happen. It's solid. It doesn't matter how long you wait. It might be softer, but it's not melting. Okay, and yet visibly melting, and yet the melt actually has started, because the scientific definition of melting is more accurately defined by this endothermic process here. Okay. The next property is solidification shrinkage. And this is very important because waxes shrink more than any other dental material, okay? When it goes from a liquid to a solid, okay? For paraffin, it's 10 to 15%, which is humongous. So it's like if you had, you know, a 3-unit bridge and you melted the wax when you made that pattern and then it solidified, well, it's going to be the size of like a 2.5-unit bridge. Okay, so that's huge. Okay. Now, of course, most materials, they shrink when they solidify, right? But there are a few that do not, right? Ice is one. So when you go from a liquid to a solid, ice actually expands. Silicon, bismuth, antimony, and gallium all actually expand when you go from a liquid to a solid. So not all solids, not all freezing, not all materials shrink when they freeze, okay? But anyway, for waxes, our problem is the shrinkage, right? Furthermore, the change in dimension is not consistent throughout the temperature range, okay? And that's because of you have so many different mixtures of different chemicals and polymers in there. And it gives rise to multiple solid-solid transformations that we will look at. And this allows us to mold waxes in its plastic state, not in the melted state. Okay? And we'll talk more about this. So in this graph, what we have is expansion, percent expansion, and the temperature. And you can see that as you heat it up, you don't get a straight line. You get like curves, and it's not consistent all the way through. And you do have straight portions, right? there are times when certain waxes will have multiple breakpoints where there's one coefficient of expansion, thermal expansion, and then once you pass a certain temperature, you have another one, and then a certain temperature, and you have another one. And those kind of correspond to different glass transitions for different parts of the wax, and that's why we have that. So the shrinkage and expansion is not as easy as most materials. Okay, Carnauba has a very low coefficient of expansion, and it's because of the strong secondary valence forces due to the high concentration of ester bonds on here. Okay, so that allows it to act more normal, I guess. Okay? Waxes also have the lowest thermal conductivity and diffusivity of any dental material that we use. 1/3000th of silver, 1/10th of enamel, and that's why you need to heat waxes really slowly, okay, so that the heat actually moves through the wax. Otherwise, you might get melting on one side and not realize it, and then you'll get a lot of shrinkage when you then cool it down again. Again, sometimes melting is not visible. Okay, so it's really important that you be patient with your wax. And in your labs, you use a drip wax technique, so you just go ahead and melt it, so it doesn't matter. But when you're actually making patterns and things like that, you're not supposed to do that. Okay, so just remember, heat the wax slowly so that it's thoroughly heated throughout the whole material. The next property of waxes is the solid-solid transformation. And I talked about molding into plastic state. So at low temperature, the structure is of an orthorhombic lattice, and it's very rigid, you know, like glassy. Well, it's not glassy because it's waxes, right? But analogous to the glassy stage under a glass transition. And as the temperature increases, it goes through a transition into a hexagonal structure, and it makes it moldable, but it has not entered the melting temp range yet. So it hasn't melted, but you can actually mold it. It's softer, it's moldable, and you won't have that problem of huge shrinkage as you go from a melt to a solid. So that's why when you mold wax, it needs to be done in this stage before the melt, before entering the melting range. Okay? The next property is flow or creep, and we talked a little bit about that last week, right? And basically, you know, obviously with matte waxes, I'm sure you've played with waxes. You know, if you just hold it, apply a small force onto this, and just leave it there, it's just going to flow. Okay, and this is how they actually measure flow. It's really not very accurate, but they have a defined force on a piece of wax that has a certain dimension, and then they just look at how quickly it flows. Okay, so what you end up getting, is this. So as you increase temperature, right, the percent flow, okay, increases drastically for waxes. Okay, in this case, it's paraffin, and as soon as you pass, what is that, 30 degrees, it just flows really quickly. Okay, and then you have this is carnauba on the other opposite end. It just doesn't flow until a very high temperature, and then you have beeswax. Okay, and one reason why it's used in the dental waxes is because if you look at the temperature, once you hit about 40 degrees, okay, then it starts to flow. So what you can do is warm it up, mold it, put it in the patient's mouth at a temperature that's slightly above mouth temperature, so you don't give them thermal shock. And then when inside the mouth, it'll get to body temperature at 37, at which time it doesn't flow as much. Okay, and this is Kerr hard wax, which is a dental wax, and that's what they're exploiting as far as usability in that dental situation, clinical situation. Okay, so adjusting the temperature at which it flows is very important. This is another way of looking at it. So this is time, and at different temperatures, you can see how quickly, as you increase temperature, how quickly the wax flows or creeps, and it's related to the moldability, right? So, okay, I'm sorry, there's a question here. Can you clarify the difference between creep and flow? There is no difference. There are two names for the same thing. The creep is the more scientific term. Flow is a little bit more layman's, okay? So, good question. Another question, creep is used in regards to metals and flow is used for flowable materials such as wax or. Well, that's not true. Creep is used for polymers all the time. And as I said, they are used interchangeably with flow. Okay, all right, let's move on. Okay, the next property is ductility. So we talked about ductility, which is how much plastic deformation or plastic strain a material can have, right? So the larger the plastic strain, the more ductile a material is, okay? With waxes, okay? Now, ductility, another clarification here with flow and creep is ductility is kind of like the instantaneous expansion or deformation, okay? Flow is over time, okay? So there's a time element to flow and creep, and for ductility, there's no time element, okay? Anyway, with waxes, if the wax has lower melting point, but they don't have melting points, right? So if the lowest part of their melting range is lower, then those materials tend to be more ductile. Let me say that again. The lowest temperature of the melting range, if that is lower, then that material tends to be more ductile than a material that has a higher melting entrance to the melting range, okay? Also, if a material has higher melting range, in other words, a wider melting range, it might start at 30 degrees Celsius and melt ends at 80 versus another material that has 30, starts at 30 degrees Celsius but ends at 50, the one with the larger melting range, broader melting range, has higher ductility. Okay? The next property is stress relaxation. And this is this graph is a little bit confusing, so I'm going to try to explain this a little bit slowly. So stress relaxation is when you, whether the material is melted or not melted, when the material is molded, and let's say you put a force or a stress on it, okay, and you mold it, it actually will have forces that are frozen in to the material, okay? So let me use this graph to illustrate that. I have this little bar on top that I can't get rid of. Let's see, let's hide presentation. So if you have, I think this is the annealed curve. And what that means is that if you have a blob of wax and you heated it up, okay, so it expands, and then you just cooled it down, it just contracts. Then you'll see that the dimensions change, right? It expands and then it contracts, okay? Now, when you heat it up, let's say you put a compressive force on it, you squish it, and then you held it and you cooled it down, okay? You would have frozen in some stresses into that material. So then the second time you heat it up, it actually will expand even more, okay? Because the frozen in stresses will push each other, the chains will push each other further away because of the frozen in stresses. So it'll add to the expansion that is caused by just the heating. Okay? So that's why when it's molded in compression and you heat it up again, this is what happens. So the opposite will happen if you put it in tension. So you heat it up the first time and then you stretch it put it in tension, and then you cool it down. And then when you heat it up again, then because of the frozen in stresses, the molecules will actually not expand as much. In fact, if you are able to give it enough tensile stress and freeze enough tensile stress, it'll actually contract. Okay, so this shows the effect of frozen in stresses when you mold waxes, because you're going to heat it to mold it, right? And that has implications for the clinic and dental dentistry, because for one example, let's say room temperature, you heat it quickly, you shape it, and here you'll see that here you have a compressive force, you have a tensile force there, and as you cool it down, these forces are frozen in. And then over time, even though if you don't heat it, over time, this frozen in stress will relax. Okay, and so with this, and you actually get a distortion happening. And so you have problems with dimensional stability with waxes. Okay, so it's important to heat slowly. Don't heat it too much, and then you shape it, and you hold, do it slowly, and try not to put too much stress in there. And be aware that there are frozen stresses, and waxes are terrible with dimensional stability. Yes, I think somebody was going to ask me a question. Alphonsus? No? Okay.
Oh no, I just got cut out and I had to come back in.
Okay, all right. And the last part of the lecture really is something that you can just read from the handout. I'll just kind of quickly skim this. And just the properties of different waxes. I have tables for you in the handout. And here I'm just going to point out a few things. Basically, for inlay pattern waxes, you want low thermal contraction, okay, because you're shaping it, right? And the pattern and the accuracy is important. Correct flow properties, which we'll talk about in a bit. Easy to carve without chipping or flaking. Clean burnout, because you're going to be using this in the lost wax technique. Color to contrast with the tooth or die. Okay? And you have the direct and the indirect type, okay, for inlay pattern waxes. And in this case, you're forming the pattern inside the mouth, okay? So you want full softening within 5 degrees above 37 degrees Celsius, so the patient does not feel uncomfortable. And at 37, when you in the mouth, you want it to flow. You don't want it to flow much at all. Okay, so it holds its shape. Indirect, you want it to soften at a little bit lower temperature because you're going to make it outside, all right? And so they have slightly different flow properties, as you can see here, with respect to temperature. For casting waxes, again, slight degree of tackiness. You're going to manipulate it mostly at room temperature, so you don't need to have low flow at body temperature. It just needs to be ductile at room temperature. Okay? So you can see that a lot of these properties have been adjusted for its different uses. And finally, base plate wax. These are some of the properties. The dimensional changes are very important for base plate wax. I have a lot of cross residents doing research with me, and I've heard case times when they're in the lab the wee hours in the morning because their dentures don't fit. So you would think you just basically make it into the shape of the mouth, the tooth, and just put it on there and it should work. It's not. The patients are very sensitive to dentures that don't fit very well, and that's actually the #1 reason for denture failure. It's that it doesn't fit, and patients get sore spots and things like that. So the dimensional changes are very important for base plate waxes, since it's used in making or patterning dentures. Okay. That's the end of the lecture for today. Are there any questions? Are you still awake?
Yes.
Okay.
I had a question actually about so the #1 cause for the denture failures is that they're not made in accordance with like those dimensional or the stress changes that are frozen in or whatever, and they just kind of over time change the way they fit and that's why they don't fail, or what exactly were you trying to get at?
Well, oh yeah, I was just saying that one of the big problems is that when you make the denture, they don't fit. That's the dimensional accuracy part. So that's why the dimensional changes for base plate waxes are important, because you have to have the pattern correct. So that's just all I was saying. Yes, and dentures can have stress relaxation, although they do use cross-linked PMMA now, and so because of that, it does much better with warping and dimensional instability.
Thank you.
Dr. Wang,
Yes.
do you mind going over slide 63, the physical and mechanical properties of stress relaxation? I got cut out.
Yeah. Oh, there you go. I think you sound better now. Can you repeat that, please?
I said, if you don't mind going over slide 63.
Slide 63.
Yes.
I don't know if my 63 is this corrective wax? What is it?
It says physical and mechanical properties, stress relaxation.
Okay, stress relaxation. Okay. So are you talking about the graph?
No, the one where you had the
or the next slide, this one.
Yes, this one.
So basically in this situation, you heat up the material, you heat it quickly. So this part is cold and this part is hot, right? So you didn't allow enough time to have the whole thing heat up. And on top of that, what you did was, oh, well, not you, but I mean, if you shaped it, molded it, then what you would have is a lot of frozen in stresses, okay? Just by, shaping it and, having heated and then shaped it. Over time, because of the frozen in stresses, and in this case, it's a compressive stress, that stress will relax and push it out, okay? And so you get this warping. And this side, it's molded in tension. And over time, that stress will relax and you'll get kind of like a compressive force. So together, it'll work to warp your wax pattern. Did that help?
Thank you.
Okay. Any other questions? Okay, in that case, let's have our quiz. And I think I need to, oh, maybe not. Okay, so let's have our quiz. This is the first time I'm doing quiz here. So let me just make sure that I have everything set up properly. Okay, so the quiz should be available. Do you see it? Can somebody let me know if you see the quiz? It's called BM Quiz 1. No? Oh, I'm sorry, it's not published. Okay, I just published it. Sorry about that. Do you see it? Yes, no? Yes, good, thank you. Yeah, I'm kind of going back and forth two different windows right now because the quiz is on a different window. So what we're going to do is I'm going to give you the on Canvas. Yes, try refreshing the Canvas quiz and it's there. Okay. Section. So it should be, the quiz should be BM Quiz 1. Yes. Yes, you do use lockdown browser, please. And yes, we can take a short break if you'd like. Let's do that. Let's come back at 10:30, and then we'll take the quiz. And then, okay. All right. So we'll come back at 10:30 and then do the quiz.